Okay, so this is kind of the last little thing that we need to look at with confidence intervals. Now, just be aware, all the confidence intervals that we look at in this course are always symmetric, and they always look from the perspective of a mean. So we're trying to find a population mean within some given data. Okay, so we're constructing a confidence interval for the mean. Now you might see, so for example, if you look at the textbook for this course, or if you just go and look away at it online, you may see that there's another type of confidence interval that you can form, which is for a proportion. Now, like I say, we don't worry about that in this course. We simply look at it from the perspective of a mean. Okay, good. So let's have a look at this in a little bit more detail. So the last thing that we need to look at is what happens if we want to find a difference in means. Okay, so a difference in population means. So for example, okay, and I think the best way to describe this is using an example. Let's suppose we have two types of batteries, okay? So let's suppose we have battery A, and we know that battery A, let's say that this is X1, okay, so battery A, so X1. Let's say this is going to be normally distributed, and we know that it's got some kind of mean life, so mu1, and it's obviously got some kind of variance, okay? So it's got some kind of variance there. And likewise, we might look at another battery, so battery B. So this is going to be X2, and again, this is going to be normally distributed with some mean, so mu2, and some variance, so sigma 2 squared. Okay, so what I might want to do is look at these two batteries. So, you know, you can imagine two different types of batteries, maybe, you know, two different brands, and we want to see if there is a difference in the mean lifetime of these two batteries. Okay, so in other words, we want to look at the difference in mu1 and mu2. Okay, now obviously if the difference is zero, then it means that there is no real difference in these two batteries in terms of mean lifetime. Okay, but obviously if the difference is not equal to zero, then obviously that might mean something else, like there is a difference. Okay, one might be greater than the other. So here's what we need to do. So really we've got three options. Either mu1 is equal to mu2, okay, so the two mean lifetimes are the same, in which case the difference is equal to zero, or the mean lifetime of battery 1 is longer than the mean lifetime of battery 2, in which case if I do a bit of rearranging, so I take it over this side, mu1 take away mu2 will now be greater than zero. See, I just take away mu2 from both sides. Okay. The third option that we can have is that mu1 is less than mu2. In other words, the battery 2 has the longer lifetime, in which case mu1 take away mu2 we'll have to take away mu2 from both sides, less than zero. So these are the kind of three situations that I want to look at. But really it stems from the fact that I'm looking at the difference in how long each battery lasts for. So the difference in the mean lifetimes. Okay. So first things first, I'm going to go out and I'm going to select a load of samples. So I'm going to select some number of samples for battery A and a number of samples for battery B. Okay, so I'm just going to collect some different, I'm going to select a load of batteries for battery A and battery B. You notice that I'm not necessarily saying that I have to collect the same number of batteries for each sample. Okay, so I could select 100 of battery A and let's say 200 of battery B. Okay, it doesn't need to be the same sample size. So then what I need to do is I need to put this together. Okay, so I need to then put it together to form a new distribution. So if you like, a collective distribution. So I need to create a mean for battery A of these however many batteries I go out and collect. Okay, so this will be normally distributed with the same mean, but this time the variance, okay, so the variance is going to be sigma 1 squared over n1. So hopefully no kind of surprises there. Okay, and likewise for battery 2, similar kind of thing. I go out and collect sort of n2 lots of this battery, and I put it all together, and I still get a normal distribution. The mean is still mu2, but again the variance is sigma squared over n2. Okay, so hopefully you can see that. So I've literally just done the central limit theorem on this. So really we just need to look at this side now. Okay, so let's have a think about this. Let's have a look. Okay. What I now need to do is think about, well, what about if I have a difference between these two random variables? Okay, because I'm looking at differences, right? I'm looking at differences between the lifetimes. So in other words, I have a mean sample here, so mean sample of battery A, so N1 lots of battery A, and I take a sample of those and put it all together, and I get this, and I want to look at the difference with that. So I'm literally just looking at the difference in the two random variables. So the central limit theorem, if I take all these samples, N1 samples of battery A and N2 samples of battery B, put it together, get these distributions, well, what is the difference? Okay, so here is my question. Okay, here is my question. Clearly, whatever goes here has to be the expectation of this. Okay, it has to be the expectation of x1 bar take away x2 bar. Okay, and I want to work out what that is. Okay, likewise, whatever goes here has to be the variance of x1 bar take away x2 bar. And again, I want to know what goes there as well. So let's have a think about this. Let's have a think about this. What would the expectation of x1 bar take away x2 bar be? Well, you know, fairly obviously, I've kind of given you a formula before. So if I said to you, the expectation of y plus z should be equal to the expectation of y plus the expectation of z. Okay, so this will come in handy. Okay, the other thing we need to look at is obviously variance. I'm just going to write it down now. So the variance of y plus z, assuming that y and z are independent random variables, then that should be equal to the variance of y plus the variance of z. And again, I've given you the proof of each of, well, I've given you the proof of that one, and I've said that that one's a little bit gnarly, the proof of the expectation is a little bit gnarly, but it is totally doable, but just accept it on face value. So this is what's going to come in useful to find each of these two things. Because as you can see, this is, if you like, just the difference of two random variables, and this is just the variance of two random variables, like y and z is. Okay? So, it doesn't take much imagination. If I want the expectation of x bar 1 take away x bar 2, okay, I can treat this as the expectation of x bar, x1 bar, plus the expectation of negative x2 bar. Okay, so I'm just kind of following that kind of idea first, because I know what the sum of them are, so I'm just going to break this into a sum, because of course if I take away, that's the same as adding a negative. Okay, so have a think. If I have another formula, so the expectation of a times y, that is equal to a times the expectation of y. Yeah, that's been seen before. Might as well do the variance as well. So the variance of a times y. Just got to be a little bit careful here, because variance is the square of standard deviation. All of those distances, so the standard deviation, will also now be squared if I stretch it by a. So I get a squared times the variance of y. And again, we've seen that before, so there's no surprises there. So really all I'm doing is just using these four formulas to see what I need to do. So have a look. The expectation of negative x2 bar, well, that's like the expectation of negative 1 times x2 bar, in which case my a will be negative 1. Do you see that? My a is going to be negative 1. So all I need to do is say this is equal to the expectation of x1 plus the negative expectation of x2 bar. Yeah? And of course if I add on a negative, that's the same as subtracting. So far there's no surprises. I mean, I kind of proved it for you, but there's no surprises there. Like, you could have said, well, that kind of makes sense intuitively. The expectation of the difference of two random variables should be the same as the expectation of each random variable, and find the difference of them. So have a think. The expectation of x1 bar is equal to mu1. Okay, we've got that up here. Likewise, the expectation of x2 bar is equal to mu2. So therefore, if I find the difference in each of these random variables, they will now be normally distributed with the difference in the mean population. Okay, so x1 take away x2, mu2. So mu1 take away mu2. There's no difference there, so I've got that now. Okay, now let's think about what the variance is going to be. So the variance of x1 minus x2 bar. Okay, so let's have a think. Well, I can do a similar trick to up here. Okay, now you might have said, well, why am I doing that? Why not just jump straight down to here? I wanted to do that, so it made more sense when I did it down here, so I'm consistent. Okay, so I can say this is the variance of x1 bar plus the variance of negative x2 bar. Okay, now we've got to be careful, because here, this is like the variance of a times x2 bar. So a in this case is just negative 1. Okay, now that tells me that when I pull the negative 1 out, I need to square it. So I say this is equal to the variance of x1 bar plus negative 1 squared times the variance of x2 bar. That makes sense because I've just simply said a is equal to negative 1 and I've pulled that out to get negative 1 squared. But of course negative 1 squared is just positive 1. So therefore this should be equal to the variance of x1 bar plus the variance of x2 bar. Okay, so we've seen that before. There's no surprises there, right? So this is different, okay? We set up here with the expectation of the difference of the two random variables. This is the same as the expectation of x1 bar, take away the expectation of x2 bar, okay? But with the variance, because the variance is a measure of the square of the standard deviation, when you pull that negative 1 out, you also have to square that using this idea up here. In which case that becomes positive, so therefore you end up adding them. So actually it doesn't matter whether you got the variance of the sum of two random variables or the difference of two random variables, you're always going to end up adding the variance of the two individual independent random variables, assuming of course they are independent. So really, x1 bar is just going to be sigma 1 over n1 like this. So sigma 1 squared, over n1. That's the variance of x1. We found that up here, okay? And then we're going to add that to the variance of x2 bar, which is just sigma 2 squared over n2. Okay, so the thing which goes here is going to be this formula here, or expression here rather, sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so that is going to be the variance of the difference of the two random variables. Okay, so this thing here, I could have just given it to you, and in fact many people do just give it to you, but I think it kind of falls back on things which we've looked at before. So you remember when we were doing the expectation and the variance kind of algebra, okay? You were like, oh god, this is so boring. But actually the reason why I spent so long doing it is because it's come up, well, I can think this is now the third time that this has come up, okay? It's really, really useful with proofs. So unless you look at expectation and variance algebra, this is pretty much impossible to do. And likewise, if I'd have given you that horrible formula for variance, you'd be like, hang on a minute, what? Right, you would have probably shouted at me, okay? But actually here you can see it makes complete sense, okay? Why do you have to add it? Well, because you're pulling out negative 1 squared, so it has to be adding it, okay? So hopefully that makes a bit of sense.